So today's webinar will be about the string design configuration. So in case you have any questions during this session, don't hesitate to ask it in the chat box. We will answer it after this session. So this webinar will be more technical, I suppose, and I hope it will be useful for all of the audiences here. So let's just start with it. Okay, so like everybody probably knows, basic principle of inverter string design. Let's suppose we have like a DC-AC ratio, and considering that we are using modules per string, and we are also using many strings, we have the option to set the number of strings or the used MPPT based on our needs, or based on the location, or based on other configuration. But what we would like to say is that for the inverter itself, also it was mentioned in the last webinar, that usually the higher the number of panels in one string is better, because the number of panels in one string, it has a direct correlation to the voltage of the string, and I will tell you why it is also better to use higher number of PV panels in one string. Just in this example, we have actually almost the same DC-AC ratio. We are using 440 watt mono panel, 30 pieces for each string, and let's suppose we are using 16 strings for this 185 kTL inverter. And for the other, we are using 27 strings per each strings, and there are 18 strings used. So by this, we are left with 1.33 DC ratio. So it's almost the same, but still, I will show why this one is better. So how many modules should be in a string? One might ask. So usually what we have used in the past is based on the following IEC standards. The first standard which came out is the I think this one, the 62548, and it was released in 2016. And there only these things are mentioned, that we need the VDC max, so the maximum DC voltage, and we have to divide it by the open circuit voltage of the panel, modified by the coefficient number of that panel related to the open circuit voltage. And for the other case, when we are calculating what is the minimum number of panels, we have to take into consideration the startup voltage during the maximum temperature, so during probably the summer, because in that case, the open circuit voltage will be lower than during the standard conditions. So this is what it is used. What important thing is also that for VDC, so the maximum voltage DC, is you have to take into consideration either the inverter voltage or the panel voltage, which whenever is the smallest one. But if we think about this, it doesn't take into consideration that probably the VOC, so the open circuit voltage, will be different in different conditions, or that the PV panel also has a correlation. If there is sun, the PV panel will have different temperature, so it will heat up during sunny weather. And also, one important thing to mention is that the so-called PID effects, so the potential induced degradation, has a sort of effect on the VOC. And as you might see, that this is actually a screenshot from one of the PV module supplier, that for different irradiances, the VOC, the open circuit voltage, is different. I don't say that there's too much difference, but still certainly there is a noticeable difference. And what the new standard introduced in 2018, the IEC 62738, is that the lowest expected operating temperature shall be the mean of annual extreme low temperatures. Use of the record low temperature shall not be required. If sufficient data is available, the mean data can be limited to sunlight hours using very low threshold for irradiance, for example, 10 watt per square millimeter or less. It also interprets that lowest temperature always happens usually at night when there is no sun and the panel has no voltage, no output voltage. And yes, so this is what the new standard introduced, and also the evaluation of module cell voltage as a function of ambient temperature and irradiance as the sun rises. So it is I think it is quite a difficult topic, but I hope I can explain in the next slides that how maybe it can be interpreted and how it can be evaluated. So there are different approaches for calculating the thermal behavior of the PV panel. First, we start with the with the one mentioned in the PV Syst. Is that in the PV Syst help manual you can find also the same information. So in the project design, array design and system losses, and array thermal losses. And there is a detailed calculation how to do the calculation for the cell temperature. So if we suppose that we have this equation, this will have a result exactly the cell temperature, and it is the function of the ambient temperature. It is the function of the thermal loss factor of the PV panel, and also the absorption coefficient of the panel, and the irradiance and the efficiency of the panel. So if we look at and if we look deeper, what is this U number? The U value is that it's made up from the thermal behavior and thermal loss factor of the PV panel, and it is used for different wind velocities, and what the number that most users have said that it's correct for this calculation during such conditions when there is no sea around and no heavy winds, is that this UC number is 29, and the UV number is 1.2 watt per square centimeters. This value is. So using these values and putting it into this equation, and also using the conservation law for open circuit voltage, we are left with this equation. Okay, so now this is the equation that we will use. Now the different approach is the NOCT method. That the NOCT parameters are also mentioned in the PV panel datasheet. So the NOCT method that you can see the references, and you can even search by yourself for these equations. This equation is stated. So also the cell temperature will be the result. We have the ambient temperature, and we have this NOCT, which is the operating cell temperature, minus 20 dividing by 800. So it seems that it's like something, it's an empirical equation, not by theoretical calculation. And also the solar irradiance. And again, we have to use for open circuit voltage using energy conservation law. So we introduce the efficiency, which is the efficiency of the panel. And if you take one example with one panel, and as I mentioned, we will introduce the U number as the following. That corresponds to 3 meter per secondum velocity of wind. Um, and we put the numbers in, the values in. For the same panel, using these numbers, we have this result. So it means that for example, I have to think about this. If we insert the 1000 watt per the 1000 watt per square meter, the cell temperature will increase by 33, yes, by 33 Celsius. It means, so ambient temperature plus 33 will be the value for the cell temperature. And for the second approach, we also use the same panel as a default. Efficiency is 20%, and the NOCT number could be 41 plus minus 3 degrees. So also using the same, we are left with the same equation. So it means that even we have used different approaches, we are left with the same equations at the end. So this actually verifies our assumption that this calculation is valid. So the next one is, because now we have calculated the cell temperature, so now we have to calculate the VOC, the open circuit voltage, based on the different cell temperatures. So we have this single diode module here. It is used frequently in the semiconductor business. So in this we have T as in Kelvin, the temperature, the key with the Boltzmann constant, N is the number of cells per modules, the Q is the elementary charge, the IL is the short circuit, and VOC, that's the open circuit voltage. And we have this I0, this is the constant for diode reverse bias saturation current, which is actually stated by the manufacturers, as you can see here. So if we insert this value into this equation, we are left with this quite long equation. And from this equation, so we state that the open circuit voltage will be the function of irradiance and will be the function of temperature. We can now calculate what is the minimum voltage and what can be the maximum voltage, and we can divide it. We can divide these two numbers, and we are left with the minimum number of cells, the minimum number of panels in one string, and the maximum number of panels in one string. So first, let's start with calculating the module number based on constant ambient temperature. Like suppose that the minimum ambient temperature in one place is 10 degrees Celsius. This is something around, not in the it's the Middle East area. There usually this number is valid. So this has to be modified according to the locations. So if we calculate with this, and we are using again a 440 watt mono panel with the short circuit current of 11.46 and a VOC of 48.9, and the coefficient number is minus 0.28% per the degree of Celsius, and we use the Sun 2185 KTL, which is certified for maximum DC voltage of 1500. But as it also has a tolerance in this maximum DC voltage, it can actually bear with 1550 volts without any damage. So based on this, the VOC values can be calculated for different irradiances. So as you can see here, for different irradiances with constant ambient temperature, we are left with different module temperatures, and based on that we can calculate the corrected VOC. And as you can see here is that as you can see here, during the irradiance of 450, In that case, we will have the largest VOC, even though this is not 1,000 watt per square meter and not the lowest number, but it means that in this case, the temperature is so it means that the panel receives enough light to have the largest VOC, and we have to calculate based on this. And the final number that what we can put in one how many panels we can put in one string is 31. And now we can also do the calculation, which might be even more close to the real situation. Is that when we take into account the historical irradiances, and for these historical irradiances, the ambient temperatures. So this should be actually used from PV Syst. So you can export the early meteorological data from PV Syst, even for the past 20 or 30 years. And you can also apply the same calculation method, what I just introduced 2 slides before, and based on the different ambient temperatures and the correlated irradiance, you can calculate what will be in those cases the maximum VOC. And now you can see that now the situation has been changed, because now the corrected module VOC is 46.87, and in the previous case we had 47.44. And so it means that we are left with 32 number of panels. This method actually used in the Far East Asia, so in India, for example, and they have been using it for the past 3 years. And based on those based on the simulations and based on the real tests, it seems that this calculation is quite valid and quite close to the real numbers. Okay, so I mentioned that why. So I mentioned that we have to go for higher voltage in the one strings. So where does it come from? One might ask, and this is actually based on the bus voltage of the inverter, and also the maximum efficiency during maximum power point operation. So for string inverter, central inverters, usually the maximum efficiency is at around 900 or just below 900 volt DC. This is due to the fact that if we have the root mean square 2 times 600, which is the AC voltage, and with some tolerance, we left with 888 volts. But for our string, the maximum efficiency is at higher number. So it means that we need higher panels in one string to be in the highest efficiency range. And it can be validated, and the calculation comes from also root mean square 2 times 800 watt plus 4 volts as tolerance, and now we are left with 1171 volt. And as you can see from this graph, this blue line correlates to almost the 1200 watt, and this is the largest efficiency. And for central inverter, the very dark blue color relates to the 870 watt, which is there the maximum efficiency. Okay, so what we can gain is based on also the studies. If you also use the same location that we used previously, where the lowest temperature is 10 degree of Celsius, and the module is 400 volt, 440 watt. Now we can calculate what will be the MPPT voltage in different cases. And as you can see, string length from 24 to 28 will be probably a better match for central inverters. And for string inverters, as you can see here, from 29 up to 32, the MPPT voltage will be in the range of the string inverter efficiency. And this is the array voltage distribution. It starts from 800 and goes up to 1100 for a 27 panel for each string, and for 30 panels in one string, it will go from 1000 up to 1200 watts, and the distribution is looking like this. Based on the calculation and using the inverter efficiency, which can be calculated based on this, and this number is also present in the previous list actually, it comes that the specific production will be higher during the 30 modules per string scenario, as you can see here. So in the long run, it's always better to use longer modules per string. And also, this was about yield. But the other case is that if we are using more strings, less strings, but longer strings, it means that we can save on cables. We can save on the module, the structure, and the mounting structure, or like the tracker cost. So this is just a short calculation also for these two scenarios, 27 and 30 modules per string. And actually there is a reduced CAPEX of $0.006 per each watt AC. So this is actually, if you are calculating in larger numbers, so in a larger power plant, this is actually a significant number. Okay, so we are done with the theoretical part, at least. We can go to the module orientation. So what we have seen and what are the typical module orientation. So we have two cases actually. So portrait or landscape, and as you can see here, this is also from a study, that this is the case when somebody mentions that that landscape is better, so that the power is more quantified because of the shadow. So when the shadow is casted on the panel from the different rows, and if you are using panels which are oriented landscape, you will have more power, because you don't lose that much power due to this shading. So for the fixed structure, what is the typical orientation is 2-row portrait or 2-row landscape, 3-row landscape, or 4-row landscape. For tracker plus monofacial, the typical orientation what we have seen is 1 landscape, 2 portrait, 2 landscape, or 3 landscape. For tracker plus monofacial, the typical module orientation is 1 landscape and 2 portrait, and also 2 landscape. But actually what we have seen is the 2 portrait is the most used I'm sorry, this is not for monofacial, this is for bifacial. This is a mistake. So tracker plus bifacial, the 2 portraits is used. I will explain in the next slide why now this is the case and not the other, not the landscape, because actually it seems it's a better idea. But this is not that easy. So as I told you, for bifacial, the power is also coming from the back side of the panel. It means that the irradiance is also depending on the closeness to the soil, the closeness to the ground. And the more closer you are, it means also not the more closer, but the first point, actually the power is larger than in this second point. It means that in this settings, so in this configuration, when you are having when you have bifacial plus tracker, you might better to use portrait mode, because you might get more power from the other side, so the back side of the panel. So as I told you, the reason for these orientation differences is because of this shading. As you can see here, so due to the bypass diode that is included, that is inside the PV panel, if the shade comes, it will cast shadow on the panels, and it will significantly affect the yield of the panel. But in case you are using a landscape, actually just so yes, we might lose one panel or like some portion of the panel just because of these the bypass diodes, because they are actually placed according to this. So like for example, 3 diode is placed, they have these bars, bars. So in case you are using landscape, you will have larger yield only just because of the structure of the structure of the panel. So based on our testing with landscape, you can reduce also the module mismatches because also the shadow. So you will get 0.4% more yield. And for in case you're using a so-called separate or a C type or spread, not separate, sorry, spread. So there are spread cables. It means that each row will get its own cable. It will go through and then it will go back, and the next one will go through and it will go back. It can also reduce the mismatch because usually there is higher temperature on the neck closer to the ground, and the velocity of the speed is higher here, and also um, due to this fact, the temperature of the panel is lower at the higher at in the highest position. So by making these cablings and making the strings, you can get more yields, even up to 0.7%. So model orientation and the CAPEX configuration and the CAPEX relation is that actually with portrait, you can save on the CAPEX, and for if you want to have more yields on the longer run, the landscape orientation might be better. So as I told you, this is the spreading module wiring. So it means that each one row will get its own cable, and it will be reversed from the back, and you are using quite a lot of cables back to the inverter. But as I mentioned previously, this is actually good for the yield. But if you want to focus on the capex, you should even change to the C type, which is not a division made by row, but it is divided by left and right, for example. And even the best solution with portrait mode is to use this leapfrog module wiring. So you are not connecting each module next to the one, but you are actually using the cables already prefabricated to the panel and connected to the other panel, which is not next to the panel. And by this, you can significantly reduce the additional cables that you are using. So just an example here, if we had a solution 1, which is this one, we have solution 2, this one, and solution 3 is the leapfrog module wiring. You actually are left with, for a 1 megawatt power plant, you are left with almost 1.5 kilometer less cable, which is quite less, quite significant here. Okay, so increasing DCAC ratio or changing DCAC ratio. First, let's see DCAC ratio definition. So it is the module's number peak power at standard testing conditions divided by the inverter total rated power. Okay, so as an example here, we have 440 watt panel, 16 strings, and we have 30 panels per each string. We multiply it and we divide it by the inverter rate power, and we are receiving 1.32 DCAC ratio. If you would like to increase the DCAC ratio, but you don't have more strings inputs in the inverter, you can use the Y connector. So the 185 kTL inverter, you have 18 strings, so you can connect 18 strings directly to the inverter. But if it is not enough and you would like to have even more, this Y connector, which we are able to sell, comes in this picture actually. So there are 4 items shipped. We have the Y connector with the fuses. This is for positive side. We have Y connector without the fuses for the negative side, and we have a one-to-one connection for that string input, where we are not dividing the string, so only one string connects to it. And we also ship some connectors. These are a technical specification of the Y-branch connector. Um, Although it mentions 1000 volt, but it is also capable of doing 1500 watt for sure. So the wiring is looking like this, is that we have the string connection plus minus the first string connection and the second string connection. And you can divide this first string connection by using the Y-branch connector. And in reality, this is how it looks. So we have the first string, the first string's minus plus part connects to this part, and the second string plus part connects to the other side of the Y-branch connector. And what we recommend here is that you are advised to use or advised to connect the Y-branch connector not directly to the inverter, so not directly like this, because in case there are some misconnection or like any installation problem and something happens, it's better to leave the inverter far from any problem. So we recommend to have some clearance compared to the inverter, like 3 or 4 meter. So just before 3 or 4 meter, you should introduce the a cable right here, and then connect the Y-branch connector. And also prefer if you evenly connect the Y-branch connectors for each MPPTs controlled by DC switches 1, 2, or 3. And also the maximum strings that you can connect now with the Y-branch connector is 27. So for each strings, for each MPPTs, you can connect even one extra string. So 9 MPPTs, 18 strings plus 7, so plus 9, it equals 27 strings in total. So what fuse should be ordered when somebody takes the order? You have to take into calculation the maximum fuse rating. This maximum series fuse rating is mentioned on each data sheet of the panel. So in case you have one with 15 amps, you have to order the one with the 15 amp fuse included, or if you have 20, you have to order the 20 amp. And also one important thing regarding these fuses, that inside the inverter, there are still no fuses, and there will be fuses only connected to that MPPT, where you need to use one extra string. And also because the fuses are in general manufactured in a way that they have a kind of tolerances, and they don't tolerate actually heat. So this is actually a good thing that the fuses are not inside the PV inverter, because the PV inverter also emits heat, so there are heat inside the inverter, so there is no heat disturbances for the fuses inside. So it will be outside, so the temperature of the fuses outside of the inverter will be more even, so it will not affect the production and there will be no problem. Okay, so how many strings can you connect to one MPPT? Due to the fact that so for each MPPT, usually we connect strings in parallel. So because it is in parallel, we have to take into account the resultant short circuit current of each strings. So the ISC, so we have to add the ISCs of each strings. And if we have an example, 425 watt panel, monofacial PV panel, the short circuit current for that PV panel is 11.22 amp. And if we connect 2 strings, it means that it will equal 22.44 amp. For 3 strings, it will have 33.66 amp. So to make the comparison, the inverter value from the inverter values, the maximum short circuit current per MPPT must be taken into consideration. So during design, uh, you have to. This is actually the second value that you have to calculate apart from the VOC, the open circuit voltage, is the maximum short circuit current for each MPPT, because these are the two limits for the inverter. This is like the design limits. If it is any of these are larger, it means that in general the internal components of any electronic device will suffer some damage. So this maximum short circuit current must not be overridden, and you want to advise not to put more short circuit current than one device can cope with. As you can see, the 185 kTL inverter has a maximum short circuit current of 40 amps. So it means that 3 times the panel short circuit current what you're using should be and must be less than 40 amps. Usually, with the panels available at the moment, this actually is not a hard job to achieve. So, as I mentioned, you have now the options to introduce more strings than 18 strings. So you have actually quite high variability in the number of strings, and you can even reach a different number of DCS ratio, like from 1.17 up to 1.80, if somebody would like to choose this number. Okay, so probably the last topic, I think this is the input current limitation, whether this is valid or not. So for the inverter that we are actually discussing now is the 185 kTL inverter H1, has a maximum current per MPPT of 26 amp. So it means that this is where when the MPPT operates, 26 amp is what it can accept for in working conditions. So what if somebody is using Y connector, and let's suppose it's a high powered panel, and the three strings combined might be larger than this number. So as current clipping is when it might exceeds the 26 amps, it must be during midday. So when there is high power coming from the sun, so there is high irradiances, it means that the exceeding of this Imax, of the maximum ampere, is at the same place when the maximum power is coming from the DC side. So usually, because there is a DC-AC ratio larger than 1, not much, but larger than 1, also in Greece or Cyprus, for example, uh, you will actually have excessive power already coming from the PV panel. So the power limitation will be happening at the same time when current limitation would happen. And when power limitation happens, so the DC power is larger than the AC power, then the inverter will set the MPPT in a different point. And in order to do this, to limit the power, so if there is 1020, 120, 200 kilowatt DC is coming, and that moment the inverter is still only capable of adding to the grid 185 kilowatt, for example. So the inverter has to modulate the MPPT point of the string of the strings connected to one MPPT. So during this power limitation, when there is more power is coming, what we need actually the string and the MPPT. I'm sorry, the string current will be less, so it will actually decrease. So just during the midday, even if you don't hit this cap, even if you don't have larger amp, the ampere actually will go down, because we have the maximum power here, and let's suppose this is larger than what the inverter is capable of accepting. So the DC power is larger than the AC out, so this will decrease. So P decreases, it means power decreases, current decreases, but voltage increases. So the voltage will be larger. So this can actually be also checked, even if the monitoring portal at this very moment, not at this moment, but in 1 or 2 hours later, if there is a lot of sun, no cloudy conditions, and the inverter operating at full power, so full AC power is coming, you might actually see that the voltage is increasing, and voltage usually increase when the temperature is dropping. But obviously during midday there is no temperature drop, even the temperature is actually increasing because it gets more sun, so it will actually have more power. I mean, actually the temperature will get higher, but still the voltage can increase due to this MPPT settings, the different settings. So by this way, the current limitation is actually minimized, and even if some current limitation would happen, the DCAC ratio, because it is not 1 but 1.1, 1.2, there will be close to zero current limitation or current clipping. Based on the studies what we have done, be above 1.3 DCAC ratio, the current limitation is actually 0. Below 1.3, it is close to 0.01% or similar to that. So this is actually the order, the magnitude of this current limitation. But also this has to be taken into account, that the inverter will drive the MPPT point in a different point during midday anyway. So this will be the topic now. I hope it was interesting for you. In case you have questions,